This screencast is all about some common reactions of alkenes. Alkenes tend to undergo addition reactions. And so, in addition reactions, the double bond will be broken and some new compound, let's give it the general formula AB, will add across the double bond. Now, in comparison, alkanes usually undergo substitution reactions where some element A, for example, might substitute for the hydrogen in the alkane. And so you'd have something replacing hydrogen in the alkane itself. So we're going to see addition across these double bonds in the case of alkenes. We can observe hydrohalogenation, and this could be with hydrofluoric acid, with hydrochloric acid, odic, hydrobromic acid, even sulfuric acid, where the species being added is really the hydrogen sulfate. So, in the case of all of these acids, what we will see adding across the double bond is we'll see the double bond breaking, and then we'll see in these available spots, the hydrogen, the acid adds to one side, and the halogen or the hydrogen sulfate adds to the other. Now, in hydration, we'll see the double bond broken, and we'll see the hydrogen water add to one side and the OH on the other. And we're going to need a catalyst for this, and that catalyst is often sulfuric acid. In halogenation, when we break that double bond, we're going to add bromine on both sides of that carbon atom. They'll actually be added on opposite sides or trans when necessary. And we can do this with chlorine. And the result is actually bromine on both sides of the double bond instead of having the halogen just end up in one spot. In hydrohalogenation, in halogenation, we have a halogen on both sides of the double bond. Now, in oxidation, we can use osmium tetroxide to add OHs on both sides of the double bond. And these will actually add on the same side. These will add cis versus the bromine we said is going to add trans with chlorine. These will add cis. Another possibility that is not as harsh as osmium tetroxide is to use potassium permanganate as the oxidizing agent. And then lastly, in hydrogenation, when we break that double bond, we're just going to add hydrogen on both sides of the double bond. We're going to need a catalyst for that, like platinum or palladium or nickel would be another option. Like nickel or platinum or palladium, we're going to need to catalyze that hydrogenation to add hydrogen on both sides of the double bond. And this is going to result in those hydrogens adding cis. So let's look into these reactions in a little more detail. Let's look first at hydrohalogenation, addition of those acids HX across the double bond. They're going to be carried out in pure reagents or in polar solvents like acetic acid. And so if we look at ethylene, we're just adding H to one side of the double bond and chlorine to the other. However, There is preference to one direction over another in certain cases where there needs to be preference. If we look at propene, propene has one hydrogen on one side of the double bond and two on the other. And there's a rule called Markovnikov's rule that says in addition of these acids HX, H is going to add to the carbon with the greater number of hydrogens already. So the hydrogen is actually going to add to this carbon where there are already two hydrogens. And that means the chlorine will add to the center carbon where there are less hydrogens. And so here's your actual product. And this product with the hydrogen added to the side with only one hydrogen is not observed. It's called the anti-Markovnikov product, and it would not be observed. So only Markovnikov's product, the one adding hydrogen to the carbon with more hydrogens already, is observed. And it's due to the stability of the intermediate that's formed on the way to the Markovnikov product. So let's look at some examples of hydrohalogenation. So let's just use HBr, hydrobromic acid. And so we already have a hydrogen on each side of this double bond implied. And so in our product, one carbon will have two hydrogens, and the other will have that bromine added to it. So we just add bromine on one side of the double bond. Or it's simpler, potentially, to just draw it like that. What if we add hydrofluoric acid here? Now we have to look carefully at this problem because one side of the double bond has one H and the other side of the double bond doesn't have a hydrogen on it. So we know from Markovnikov's rule that the side of the double bond that already has one H is where the H is going to add to, the side with more H's. And so the side with a methyl group will actually be where our fluorine adds. And so we're going to have that fluorine adding to the same carbon that has a methyl group, so that hydrogen can add to the side that already has more hydrogens and follow Markovnikov's rule. So next we'll look at hydration, addition of water across the double bond. It's acid catalyzed, so we usually use sulfuric acid, for example. And again, this one's going to be regioselective. Hydrogen is going to prefer the less substituted carbon. Hydrogen is going to prefer to add to the side that already has more hydrogens. So for example here, hydrogen would add to this carbon since it has two hydrogens compared to the other side of the double bond where the carbon only has one hydrogen. So we'll add the H to the side of the double bond that has more H's, and then the OH of water will add to the central carbon. And so if we look at the next problem, same thing. We're going to add the add the hydrogen to the side of the double bond that already has more H's, and then the OH will end up at the center carbon. So let's try a couple examples. Let's try to add water across the double bond with a sulfuric acid catalyst. We're going to break the double bond. Both sides already have one hydrogen on them, so it doesn't really matter where we add our hydrogen. We'll just end up with one OH on the molecule. What about here, though? What about 1-methylcyclopentene? We have a methyl on one side of the double bond and a hydrogen on the other. So we need the hydrogen to add to the side of the double bond that already has more hydrogens. We're going to follow Markovnikov's rule. We add our hydrogen here. which leaves our OH at that top carbon spot with methyl. So next we're going to look at halogenation, addition of chlorine or bromine across the double bond. And so the addition of bromine is a common test to look for the presence of an alkene. It's a good visual test. So let's look at the addition of bromine across to butene. We get a bromine on either side of the double bond. The bromine has this characteristic orange color that we see in the bromine water at the bottom of this test tube. Now, let's say that there's an alkene placed at the top of the test tube. When you shake up that test tube, the bromine, the characteristic orange color of that bromine water, will disappear as the bromine reacts, and it will leave it clear at the end. And so your product will be clear after it's reacted all of the bromine water. Now, if it were to remain unchanged and your orange color were to remain, then you would know that your top layer contained an alkene. But if the color of your bromine water disappears and goes to clear, then you know that you, in fact, had an alkene in that top layer. The addition of chlorine and bromine is stereoselective. It wants to form the trans isomer, and that's the preferred isomer. Because an atom like bromine is so big, this occurs in a two-step mechanism where bromine adds on one side of the double bond, and then it's forced to add to the other side of the double bond in order to really have enough space. So we end up with the trans isomer. We end up with a bromine on each side. Let's do chlorine to show another example. And we have a hydrogen on each side of the double bond. And so what we're going to make is the trans product. And so we could go ahead and show our hydrogens too. Because our hydrogens will also be trans. But it's important that we show that our two chlorines have one up and one back, that they are trans, so that we have the trans 1,2-dichloro. So trans 1,2-dichlorocyclopentane. We've broken the double bond and we've added the chlorine across the double bond. That's really been our theme here so far with all of the addition to alkenes. So next up is oxidation of alkenes. In oxidation, we add oxygen or remove hydrogen from a carbon atom. Reduction is just the opposite, the removal of an oxygen from or the addition of a hydrogen to a carbon atom. It's the way we really look at oxidation and reduction in organic chemistry. So here we're going to look at oxidation, adding bonds to oxygen. So adding carbon to oxygen bonds. We can use osmium tetroxide to do this, to convert the alkene to the glycol. A glycol is a compound with two OHs on adjacent side-by-side carbon atoms. It's stereoselective. They're going to add syn or on the same side to make the cis product. And that's because the osmium holds these two oxygens really in this intermediate where they have added on the same side of the double bond. So it's important that we just note that the product is going to be cis when we use osmium tetroxide. We can also use potassium permanganate to do these oxidations. Potassium permanganate has a characteristic dark purple color. It's very deep purple color, depending on its concentration, like this. And so potassium permanganate and water add again to form this glycol, or the two OHs, cis, on the same side. In a similar manner to osmium, that manganese ion is going to hold the two oxygens so that they are adding cis on the same side. And the manganese dioxide product that forms is really a deep, dark brown or black color. And so, if an alkene is present, the purple color of the potassium permanganate will disappear and sort of a sludgy precipitate, it's a solid precipitate that's brown-black, will start to form. If it's not an alkene and just an alkane is present, that purple color will really remain and no solid precipitate will be seen. What if we use potassium permanganate to form this diol? Well, we just want to remember that it is going to be cis. That it's going to add OHs on the same side. So next we're going to look at hydrogenation of alkenes. Alkenes react with hydrogen in the presence of a metal catalyst, platinum, palladium, nickel catalyst, and that catalyst really activates that hydrogen bond. It really weakens the bond between the two hydrogen atoms, and that hydrogen really adheres to that metal catalyst. And so, since the hydrogen is stuck on that metal catalyst, that solid metal surface, it ends up adding on the same side. So we'll add hydrogen across that double bond. We add hydrogen on each side before. Now we're going to add another hydrogen as we split this hydrogen and add it across the double bond. It is going to be forming a cis product. We're doing syn addition. And that's because that hydrogen is adhered to that metal catalyst, adding these two hydrogens on the same side. What do I mean by that? Well, let's say we had some metal catalyst, and we're going to weaken that hydrogen to hydrogen bond, activate it. And so these two hydrogens are going to add on the same side. So let's imagine these methyl groups are sort of popped up. Then these hydrogens are going to be adding below, and so they result in a cis product. My two hydrogens added on the same side because they were stuck on that surface of that metal catalyst. And so we'll end up with cis, 1,2 dimethyl cyclohexane. And so now hopefully you are familiar with some of the important addition reactions for alkenes.